My lab for oscillations. The two objectives of this lab were to compare the predicted version, the computed model that we created, with the observed motion of a mass oscillating attached to a spring, and we do this by using Newton's second law and energy principles to analyze changes to a system. Here are some of the key ideas and formulas that we use in this lab. For example, the position update formula and the velocity update formula. And of course, we have the kinetic energy, gravitational potential energy, and spring potential energy formulas, all of which added together are equal to the total energy. Some conditions this lab has is that we know that the total energy is conserved because it is a closed system, and the three energies that we're using are kinetic, gravitational potential, and spring potential energies. The first thing we did was we used Tracker to analyze the motion of the object in the x and y directions. We set the axes so that left is negative motion in the x direction, right is positive motion in the x direction, up is positive motion in the y direction, and down is negative motion in the y direction. Using these points from Tracker, I created these graphs to show the movements in the x and y directions. The top one is the x direction, the bottom one is the y direction. As you can see, both of them are oscillating movements, but both graphs are inverses of each other. And using the position data that we got from Tracker, we put that data into a CSV to help create our computational model. To calculate K, we use the period of oscillation, or T, calculated from the position data from Tracker and the mass of the object. We calculated L using the spring stiffness value. In the code, the first step was to initialize everything. We initialized the object's mass, the object's initial position from Tracker, as seen here, and here the initial velocity, which is 0 because it starts at rest. Here we have the gravitational constant, the spring constant, and the relaxed length, which we calculated from the previous slide from these two formulas. This right here is to calculate the length and orientation of the spring, and in this little part of my code right here, you can see that this one is supposed to calculate the kinetic energy using the same formula from the previous slide, or K equals 1/2 mv squared. This one is the gravitational potential energy formula, which is just m times g times delta h. And the last one is the spring potential energy formula, which is also from the first slide, and this is the total energy formula, which is just summing these three. One more thing. And here we define the initial energies for the. Okay, in this slide, here we have the gravitational force, which was calculated by just using mass times gravity. Here we are calculating the spring force using Hooke's law. Here we're calculating the net force using the formula F net equals force of gravity plus force of spring. And then we have the momentum principle, which is Newton's second law. We use the velocity update formula, the position update formula, and this is for the energy changes of the ball. This is the change in kinetic energy, the first formula. This is the change in gravitational potential energy, the change in spring potential energy, and the change in the total energy. Here we have a computational model that shows the change in energy versus time, which is also shown by this formula down here. And you see as the orange line remains constant, the orange line is what represents the total energy, which you can see remains at 0. Here we have the x and y position time graphs from the computational model. As you can see, they're very similar, but there is a little bit of a difference in both, which the oscillation is greater for the y because there is more force on the y component of the motion due to the spring force and the force due to gravity. So the energy principle is satisfied because, as the orange line shows in this graph, it does remain constant, or it does remain at 0. So the energy principle is satisfied because the change in energy equals work, and by the energy principle, the change in total energy is equal to 0. The average period of oscillation calculated for x was 1.682 seconds, and the average period of oscillation for y is 1.533 seconds.